Hello everyone. Today my topic is on traffic signal control around the world. So I'll discuss about the traffic signal control related research and practices what are going on right now around the world, and also the background history evolution of those researches and practices I'll discuss. And my research presentation topics covered evolution, adaptive control, prop vehicles. Also, I'll discuss connected vehicles and relevant artificial intelligence related research on traffic signal. I will present here. So, in the next slide, what is the motivation here? If we look at the traffic signal matters why, in North America, average 63 hours delay per person. Is Los Angeles, it is 137 hours, and economic loss is over 160 billion annually. In Europe, it is 101 hours per person, and annual cost in UK is almost 3.85 billion. And congestion level is right now is almost 51.6%. And in Asia, if we look at in Bangkok, the congestion level is 67.9%. And in during rush hour, the average speed is only 51.7 kilometer per hour. In Manila, to drive 10 kilometer, it takes 25 minutes, 30 seconds. If you look at the Latin America, annual 195 hour loss per person. In Peru, Lima. And why traffic signal actually matters? Because it reduces delay and stops, create more stops, and we have to improve safety, reliability. We have to cut fuel use and emission. We have to support buses, pedestrians, cyclists, and need to ensure smart city mobility management. So congestion is major mobility and emission problem worldwide. If we look at the historical evolution, manual traffic signal was first introduced around 19th centuries. Then comes fixed control, which use fixed timing around 1950s. And then comes vehicle actuated controls, which use real-time adjustment. Then comes coordinated signals, which is around 1970s idea, first introduced in 1970s, and it will coordinate multiple signals together. Then comes adaptive signals, and after adaptive signals, we can see the trend of probe vehicle-based control. And latest hot topic around 2010 comes the connected vehicle-based control, which use real-time data and ensure smart control. And after 2015, AI-driven control, machine learning to optimize signal to get the maximum efficiency comes in the field. Next, we can see that the signal control hierarchy, traditionally, it can be fixed time, semi-actuated, fully actuated, which use full demand responsive intersection and coordinated, use signalized arterial progression. And advanced system, we can see adaptive, which use real-time optimization, predictive to model for future prediction, prop vehicle-based method, which use floating car. Then comes connected vehicle, AI-based system, and at last we can see that the multi-agent based distributed intelligent agent collaboration comes. And fixed schedule, now the traffic control hierarchy, if we look at here, it comes from fixed schedule to AI-driven optimization and ensure smarter cities. Then comes the fixed control system, which is the classical signal timing method. Its core principle used Webster's optimal cycle length, and it is used in the highway capacity manuals and transit tools, and it is stable and its strength is simple, but weakness is poor responsive to traffic. Then comes the vehicle actuated control, and vehicle actuated control is done by loop detectors, inductive loop detectors, radar, microwave, camera, video detection, thermal sensing, and LiDAR device. Latest LiDAR device can be used. In the LiDAR device, it uses 3D high precision 3D scanning for distance, speed, and vehicle classification. And infrared can also detect vehicle engines, tires, but it also good for low visibility. But video camera is for using image processing is widely used. It can measure actually the presence count and classification. So the actuated control actually use gap out, max out, or extension logic. And its flowchart, if we look at the flowchart, we can see that it detect vehicle, then check the gap, extend green phase. If gap out or max out, then it returns to the original logic. Benefit is real-time adaptation, reduce delay, and also improve efficiency. Then comes the coordinated control, which actually promote green wave progress, and it ensure the optimal offset, ensure the optimal speed and cycle length, and it is applied in the USA, European country, Japan, and China. And if we look at the time space diagram of coordinated timing, we can see it is taken from the Federal Highway Administration. We can see that the bandwidth, green bandwidth, the primary target is to increase the green width of green bandwidth, maximize the green bandwidth. We can see in the left side, the corridor, our coordinated phases are 2. Coordinated phases are 2, 6. 2 and 6 is the coordinated signals to coordinated phase, and other phases are not coordinated. The non-coordinated phases are 1, 8, 5, and 4. But 2 and 6 are the coordinated phases here. So target is to maximize the width of green band. And it use offset, split, cycle length to ensure the green wave offset control traffic signal. Then comes here the actually little bit confusion with the languages. I have to correct it. Then comes the adaptive signal system. There are a lot of adaptive signal techniques. First comes the SCATS, which is Australia based, and it use actually the degree of saturation principle. Then comes SCOOT. It use continuous optimization of cycle, speed, and offset. Target is to minimize delay and stop. Then comes the OPEC and ROADS. OPEC use dynamic programming for real-time phase optimization. ROADS use hierarchical real-time optimization. TUC is the traffic responsive urban controller. It use linear quadratic optimal, and it use the basis of store and forward model. Then comes ACS Lite and InSync, which are United States based. ACS Lite and InSync use demand responsive phase selection, and ACS Lite use adaptive adjustment of cycle length, speed, and offset. Then motion and track. Motion is developed by the Siemens Mobility, and actually the detector use different type of detector. SCAT and SCOOT mainly use loop detectors. However, in the later, some InSync use the video cameras and radar detector, and motion use sensor detectors like loop, multi-sensor detector like loop camera and radar. And if we look at the control type, we can see that the InSync use adaptive intersection and corridor control, and TAC use centralized network adaptive, and scarce use centralized network adaptive. Most of the use the network adaptive system. Centralized network is system. However, OPEC also can use the isolated or intersection control, and ROADS use the hierarchical adaptive network control. And if we look at the deployment advantage and limitation of these different approach, we can see that the scarce require extensive detector infrastructure. However, it could depends on high communication and detector maintenance requirement. And if we look at the ROADS and TAG, ROADS use the complex implementation and high computational demand. SARTRAC also use the large scale deployment is limited. Its problem is large scale deployment is difficult. And ACS Lite, the low implementation using it use the low cost implementation using existing infrastructure. And if you look at the motion, it is applicable for the large urban traffic network, and it can predict coordination, integration with intelligent traffic ITS system. It requires specialized hardware and software that has this limitation. And if you look at the OPEC, it is computationally intensive and limited for commercial development, but it has real-time optimization and prediction capabilities is the strong point of OPEC. And what are the optimization principle? If we look at the optimization principle of adaptive signal, we can see that they use dynamic programming, also use rolling horizon optimization, sometimes which are based on the model predictive control. It can predict the short-term prediction and planning, use the linear programming, also mixed integer programming it use sometimes, and also max pressure control. Max pressure control is much popular right now, and queue balancing and network optimization is a promising sector here. It synchronize signal across network and distribute traffic loads evenly. Then probe vehicle-based control. For probe vehicle-based control, the source of data is GPS, smartphone, fleet vehicle are used, floating car, navigation app, and ride-hauling vehicle are used. And these application of probe vehicle are in queue estimation, travel time estimation, adaptive timing, and also arrival prediction is also another point. Adaptive timing, we can control, we can use adaptive timing for the traffic signal for building the smart traffic signal control and real-time changing signal. Then comes the connected vehicle, and is actually based on the V2X communication technologies. Within the V2X, vehicle to everything, we have vehicle to infrastructure, vehicle to vehicle, and vehicle to network. And communication standard, it uses dedicated short range communication, and also use cellular vehicle to everything communication, can use the 5G technology, CV2X, and application can be the SPAT and map use. We use real-time traffic signal information and geometric map for navigation, and queue estimation, also cooperative intersection management, signal timing adaptation. Transit support is another. It can ensure signal priority for the transit vehicles, and eco-driving support to advise real-time basis for driving behavior, reduce the fuel consumption and emission. Then comes the traffic state estimation. If we look at the different method that use Kalman filtering, particle filter, extended Kalman filter for non-linear model. Particle filter use Monte Carlo and non-Gaussian or Gaussian system. Bayesian estimation can be possible. Unscented Kalman filtering can possible. And also LSTM and transformer-based model, graph neural network, use graphs and complex topography. And why it matters, it turns partial observation to actionable state, and support queue prediction and phase selection, which is the key for the optimal signal timing, and it bridge or connect between probe, CV, and roadside sensor data, fuel diverse data sources, obviously it is. And then comes the artificial intelligence, and it's actually within the framework of deep learning and reinforcement learning, which are widely used. And within reinforcement learning, there are a lot of algorithm families, DQN, proximal policy optimization, advanced actor critique, and also have soft actor critique, deep deterministic policy gradient, and especially the proximal policy gradient use policy gradient stuff, and deterministic policy gradient use continuous timing, twin critique use reducing overestimation. And if we look at the right side, we can see that the reinforcement learning architecture that covers within state and action, and there is a policy or value network which work as agent, and within the state and action there is traffic response or environment, and reward is getting to ensure by smooth flow or reduce delay. And policy and value network is the agent which works together, and the reinforcement learning formulation actually works in the state action, and it is actually action is the next phase, and reward can be delay or stop reduction, and objective is to maximize the reward. Then comes the multi-agent reinforcement learning, which are widely conceptualized for the traffic control. Centralized training and decentralized execution is one concept, and also cooperative learning across intersections. Graph RL and topological aware control is also a concern, and single intersection or multi-agent RL for network level is widely used. If we see that the MRL interaction model, we can see that the traffic data and queue length, those are state information passed through the multi-agent controller. Then efficiency and delay reduction is a reward. Those are passed to the environment, and multi-agent controller take that action accordingly in between two intersection A and B. And data sources, if we look at the data sources of traffic control, loop detector is widely used, but its scalability is low. Coverage is point location. Camera is scalability is medium. Its accuracy is high, like loop detector. Radar accuracy is high, scalability is medium, latency is very low. It is the positive side. LiDAR also have low latency and very high accuracy, but scalability is medium. Bluetooth sensor has high scalability, and GPS receiver has medium scalability. Maintenance is low, but cost is medium, but it is vehicle specific. The problem is, and also prop vehicle. If you look at the prop vehicle, its accuracy is high, but network coverage is wide. Scalability is also high, but maintenance cost is low. Connected vehicle, maintenance cost is low, accuracy is high. Drone, it has medium scalability, but its latency is low. Coverage is across local corridor or intersection, same as camera, but more wide. Mobile phone data, it has high scalability and coverage is city or regional. Floating car data, it has network-wide coverage, but scalability is high, cost is low, latency is low. Drone and floating car has low latency, but mobile phone data has medium latency. If we look at the performance, we can see that the performance measures are delay, queue length, stops, average speed, throughput, pressure. Pressure is the traffic intensity, travel time, level of service in terms of driver comfort and speed, fuel consumption, emission are also considered as performance measure. Reliability of travel time is a issue, and network productivity is also a matter here. If we look at the worldwide case, we can see that Australia developed SCATS, United Kingdom is good, and USA also developed ACS Lite, SharkTrack, InSync, and China developed AI-based, working on the AI-based control. Singapore is connected intersection. Japan probe vehicle system. Netherlands use cooperative ITS system. And comparative study among the different traffic control methods. If we look at the real-time adaptability, fixed time doesn't have real-time adaptability. Actual has moderate, but SCATS could have good real-time adaptability. Max Pressure has very high adaptability. Reinforcement learning has also very high adaptability. If we look at the practical deployment point of view, actuated fixed time SCAT and Scoot has widely deployed facilities. Opaque route TUC has moderate or limited. However, reinforcement learning is mostly on research, and connected vehicle is emerging basis. And feature readiness point of view, if you look at the fixed time actuated has very low feature perspectives. However, SCAT Scoot has moderate, but connected vehicle reinforcement learning has a very excellent feature readiness. Doors TUC and OPEC has moderate future perspectives. If we look at the overall performance rating of different methods, that SCAT is mature adaptive network control, Scoot is continuous optimization, OPEC is high computational burden but limited deployment, ROADS is complex implementation, TUC is accurate traffic state estimation, but also effective for the large scale urban network control. Max Pressure has excellent throughput, but it has limitation with pedestrian priorities and fairness. Probe vehicle control system is reduced infrastructure dependence, but also require probe penetration rate. Connected vehicle is highly accurate, but need widespread deployment of V2X communication and CV deployment. Reinforcement learning has learning automatic or the self-learning system, but it has a high computational cost and require huge runtime. And if we look at the emerging technologies, within the emerging technologies, we have digital twin with virtual replica of physical system, edge computing. We can process data near the sources, cloud computing, 5G and future networks, Internet of Things, IoT, cooperative ITS, which blended with the intelligent transport system, AI-enabled traffic management, and federated learning, which use actually the decentralized machine learning properties. If we look at the hybrid framework within advanced traffic control hybrid framework, we have sensing, prediction, optimization, and control. And within control and sensing, the feedback mechanism works. And there are also within this hybrid framework, we have probe vehicle and RL, connected vehicle and model predictive control, and scarce inspired reinforcement learning, connected vehicle and max pressure control and reinforcement learning, drone assisted adaptive control, and also model predictive control, and mix up with the reinforcement learning. What are the current challenges? If we look at the current challenges, we have mixed traffic and its safety is a concern. Low connected vehicle penetration is a problem. Probe vehicle can have biasness and communication latency. Privacy and cyber security is a problem. Sensor failure due to the weather condition. Scalability is a concern. Pedestrian integration is a challenge, and public transport priority need to be ensured with the existing signal optimization techniques. And future research direction, if we look at the future research direction, within the connected autonomous vehicle, that is CAV. It also integrate with the real-time coordination and improve safety platooning, AI-based digital twins, which is ensure the real-time monitoring, scenario simulation, large language model, LLM for traffic management, trajectory prediction, foundation model, which is pre-trained large-scale model, multitask learning using CV and NPL, and graph neural network. GNN is used for the traffic flow forecasting, spatio-temporal analysis, drone-assisted monitoring, traffic surveillance and accident detection, and sustainable multimodal control. Use the optimized multiple options, reduce emission and energy efficiency, and also can ensure the seamless trip planning. Then summarize everything regarding the evolution and future of traffic signal control system. We have fixed schedules, then comes the adaptive, lastly connected and AI-based system. Need to improve the observability using the probe vehicles and connected vehicle technology. Challenges within the robustness and reliability, cybersecurity, and the cost and infrastructure is a issue. Next generation covers max pressure control, model predictive control, and reinforcement learning. Reinforcement learning, it use agent, environment, reward, and the state. And strongest future system is hybrid and multi-agent system, which is a promising sector here. And these are the references. We can see that the references which I covered to study and prepare this presentation. I have some review papers and original researches. I provided the references as the paper type, objectives, methodology, findings, and future direction, so that anyone can get information from this brief table. Thank you so much for listening my presentation. Thank you.